Next, we will talk about the entropy loss. And for entropy, with how to say, for the different order of the symbols like A1, A2, A3, A4, and so on. And usually the first entropy, like correlation dips, like if it is no correlation here, which means the first HA1, and it can achieve the highest entropy 5 bits per symbol. However, from the second symbol, and only can achieve 4.05, and the third is uh, 3.52 bits per symbol, and it shows it decreasing trend, and because for the uh, for the between the two symbols there is some another information here, and also if they consist of some um, specific order, and also here some information. So from the order go on, and the entropy will decrease. So that information will we call it as the conditional entropy, which is quite similar with the conditional probability. And if we have some normal test and the update of the 32 letters, and we can calculate the highest entropy. H max will be the log 2 base, and this we only can 5 bits, and that is only for the first symbol, and it has some deep correlation and some high redundancy, and the mutual information, and before the and we mentioned about the before the mutual. So this movie also it will have okay. And the high here has some explanation about the higher correlation and the lower amount of the information, and the efficiency also can be like this, and uh, around the 80% efficiency, and redundancy around the 20%. So it has some high redundancy. Our task which will reduce redundancy. And well, this picture shows some relationship of the uh, mutual information. If we have some uh, two symbols, a ax and a y, and each of them we have some entropy will be the hx and the hy, which in this graph, and hx we show the pink cycle, and hy shows the rose cycle. However, they have some mutual information, h, x, y, and the mutual we know, and mutual information here the I, xi, xy, and we use some method to estimate. And first we use the hx to minus with the conditional entropy here. Yeah, we use this one minus this one, we can get the mutual information. We also can use the hy's entropy to minus with the x conditional entropy with this part to get the mutual information. And also we can use this with both the entropy to minus the joint entropy. So here is not this is still the mutual information. Three formulas you can calculate the mutual information: 1, 2, 3, and the joint entropy will be here. And it can be like this. We can use this to calculate the joint entropy, which means the both of them here joint entropy, and no yeah, use the hx plus this joint condition entropy will be the both sides will get the total part of the joint entropy. Next, we will talk about the source data rate. And for the source data entropy, and it has efficiency measure. We hope to get the high-Q better and desirable to achieve the highest entropy. So our idea, we hope to get close to the maximal entropy, and the performance of the source can be data, the data generation rate. Data generation rate can use this function to represent, and m is the code word length, and tau is duration of the binary symbol. So the idea is that increase the source entropy and decrease the code length and the code word length and the duration of the binary symbol. So to achieve the maximum data rate, we need the maximum information amount per symbol. Hmax, maximum information amount per symbol, and this is, we call it the channel capacity, which is a physics elimination channel physics elimination for the data transmission speed. And so the data rate must smaller than the channel capacity, because if the data rate greater than the channel capacity, so they will have some loss, or it could not reach maybe it cannot achieve the elimination, channel capacity elimination, and the data rate usually considered the bit rate. That is our commonly used. So the idea, there are two questions about how do we improve the source data rate and how do we increase the source entropy, and the solution, which is the statistical source coding, which is proposed and worked out by the channel in cooperation with the funnel. Next, we will introduce about the optimal statistical source coding. And the goal is to compress the information of the symbols to use the fewer signal samples for the faster data transmission, which means the important part, which is the compress and the coding, the mapping of the with definition here, the mapping procedure of the source symbols or to the specific signals. Let's see, and code word, which is the a sequence of the symbols generated by coding device. Code is the law of this generation, and the length of the code and length of the code words can be the fixed or the variable. So for the fixed length code, and it has some advantages and the technical simplicity and coding decoding algorithms is quite easy. And the drawbacks are here, the maximum entropy cannot achieve in most practical cases. Because in order to fully utilize each binary symbol, the volume of the alphabet must be the two the 2 power of n, and all alphabet symbols must be equality with the 1 of the n. So it has some similar. Each symbol has the same probability here, and we can see a practical example about the code, and which is a telegraphic character encoding, which also prior to the ASCII2, and the volume of the alphabet, which is 32, and 32. So we calculated the number of the binary symbols per character, which will be this function, the length. The code word length will be the 5. And so you will see here, and the code for each character with the 5 length code word, and all the symbol of the alphabet has the same length here. And you can, if you're interested, you can just see the bold code Wikipedia introduction. And also we have the variable length code, and because the fixed length code provides no benefits of improving data rate, and we must use the variable rate because firstly it considers the statistical of the source, and for the statistical, because the source has different different probability for each symbol, and we can enable the data loss or data compression, and there is no data loss here, and no distributive compression. So for the variable length, no, here still it was to mention here is the short the short code length will for the high probability, and also for the long code length for the lower probability, because we have different probability, and the lower is the code words, which is if we want to achieve our goals, that is we must follow these laws. And for the variable length loss, we have the most well-known two code, and which called the Shannon code and the Hackman code, which it also you need to calculate in your course project task, and I will introduce about how to do that. So for the different symbols, we have different probability, and which we'll see the let's get back short code length for the high probability. So for the high probability, we'll have the short code length. Not where we are same with the like previous. We have 5 code lengths of the each symbol. Suppose we have the 2 or 3, 4, 5. That's the yeah. So like here we have the smallest 5, and we have different code lengths. That is the idea. And it requires the source statistical. And if there are no statistics available, they're just collected, and for the there these two code application, including Rubber, Zip, and all and Hackman, are many used in the graphic compression like JPEG. And for the video MPEG are most used in this two cases. So we will talk about how to do the Shannon funnel coding. And the algorithm, we have the 4 steps. So first we will sort the source symbols in some probability decreasing order, which means from the symbol we have the high probability to the low probability, and each time we divide the offset of the symbols into two groups, and each of groups it should has the equal to the will equal to the has the same probabilities and equal the total probabilities. And because we have the like two group, group 1 and group 2. And we have different samples, and each time we will we calculate the total probability, which means we just plus all of the samples together to get the total probabilities here. And we need to assign the one symbol to the one subgroup and the zero symbol to the second subgroup. And the third step, which is continue the further division of each group until the subgroup consists of the one symbol that will be the enough. And we read the code words from the left to the right. They are our laws here. So let's see. For example, we have the four symbols, and we saw them with the probability with the high probability to the low probability. So that is subgroup, the first division. Yes, this we call it the first division. What is that? First division. So, and obviously we can see here, and 0.5 will be the one group because it's quite high, and the other three will be the second group, will be the also plus them together also can be get the 0.5, and we can get them code like, how do you say, assign the 1 and the 0 to the symbol, and which is the 1, and the second the one group is 1 and the other group is the 0, and that's not for the first group because this only has one symbol. We only need to do the from the second division. And let's see. So 0.25 is quite high, and we suppose it as the one group, and we sum as 1, and other two also can equal to 0.5 as the second group, and the A. So for the third division, this also only one symbol here, so no need to code here, coding here, and we can go further to the third division. And for the here, we only have the A4, A3, just assigned with the 1 and 0 here. So, however, we cannot do that like from the, if you specify the upper group is 1 and the lower group is the 0. You cannot. You must follow this laws. You cannot replace like 1 0 0 1. No, you cannot like do that. We must follow by the previous definition, and must go on with the 1 0 1 0 1 0. So it's quite easy to understand. And now we can read the code word. Don't forget it, but from the left to the right. So the A4 only has one code word, so it's going to be 1. And the A1, we have the 0, 1. We have 0, 1. That will be the here, the A1. And we have the A3 symbols code word, how to read it, and from the left to the right, and here, and it will be the 0, 0, 1. And the last one will be the last group is 0, 0, 0. So it's not very difficult, quite easy to understand. So here is some detailed explanation here, and as I will introduce, so the first division to do the code, and second will be the last, and next we want to introduce the half-man code, which most practical and useful rather than the semifinal code, most efficiency code formatting, and still used in today's daily life. So let's talk about its algorithm. And first, we saw the similar with the previously, we saw the source symbols in the probability decreasing order. And the next step is the select two symbols with the minimal probabilities, which means the minimal two symbols, minimal two probability symbols, P1, P1 and P2, and we merge them into the symbol with the probability 3, which means the P minus 3 equal to the P minus 1 plus P minus 2. And we assign the 1 to the upper branch and the 0 to the lower branch, or the vice versa. And for the different division, it will be the same. You must follow this laws. Cannot change it. The fourth step will continue the same procedure, and considering the remaining symbols, original and merged, and stop at the probability of the merged symbols. P will equal to the 1 after we merge all, because the all symbols probability will equal to 1. And the read code words will quite the offset with the final coding, and we read it from the right to the left, and which by the following the code tree runs. So we can do it, and similar with the previously, and different symbols, and sort them with the maximum probability to the minimum probability, and let's do it. And the first time we take the two small probabilities and merge them together, will be the 0.5, and we assign the upper branch and lower branch with the upper branch with 1 and lower branch with 0. And we got this one 0.5. And the last one, after the first combination, now we don't need to consider these two. We just consider this one, this three. And we select the minimal two probability 0.5, 0.5. So obviously we should merge them together to get this part. And we also assign the code with send 1 to the loop branch and 0 to the lower branch. And we have the 0.5 and the last we only left one symbol, so we just merge them together. And we can see here we got the 1. So 1. So the total bit. So when you did your code tree, you must to be careful after the code. The of them should be the plus merge should be equal to the 1. If they are smaller than 1 or greater than 1, they are all mistake. And simply we assign the 1 to the upper branch and 0 to the lower branch. So how to read it? And it is opposite with the Shannon code, and we read it from the right to the left. So for this one first, A4, how can we read it? And it will start with here. So here. It only has 1 here. And A1 we started here. We pass the 0 and 1, so it will be the 0, 1. And for this part, and we A3 we start from here and here. No, it's still not reached to the A3. And we pass the 0 and the second 0. Finally, we pass the 1. So the code will be the 0, 0, 1. And the last one will be start from here and go here. We pass the 0, and the next is the 0, and the next is 0. So it will be the last one will be the 0, 0, 0. And next we will talk about some properties of the optimal statistical. And well, it has some compression effect. So as we talked about before, the higher probability symbols encoded by the shorter code words, and the lower probability symbols encoded by the longer code words. For the Shannon code method, and it usually allows the multiple it allows to the multiple possible codes, and need to the compare and answer. So it's not Shannon code is not and it has lots of variant, and we call it type 1 or type 2 and so on. So half-man code, which is most used most often, and it 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 has too much ambiguous. That is their uh, characteristics. And for next is uh, prefix code, and which means the um, actually the prefix code they have the relationship. So it comes from the variantness. Variantness code. It comes from variantness code, and variantness code can also better than the fixed NAS code. And for the prefix code, and it has no short code word begins any longer code, code word, and this enables the correct recognition recognition of the symbols. So if we have the code word like this one, we can do some decoding test example, try to do it. We have this one, and we can do it like 0, 1, 1, 0, 0, 1. So we start from the 1. So how many 1 has the, how many code words start from 1? So here we check it only from the A4. And for the second 0, which has this one, has lots of choice. A1, A3, A2. However, let's go on. We must choose the one is to choose the most matched symbol, and we saw the next from the here we 0 cannot make cannot decide which symbol we need, and we can go further symbol 0 1, and it showed has A1 here, so we can see the 0 1 will be the A1. You also can try to use the, how to say, 0 1 1. No, you cannot find here, or 4-bit 4, and the 4 coordinates, coordinates, and no, the highest coordinates is 3, so you only can choose this one with A1. So we choose this one, and the next day we'll start from the 1. 1 is only the A4, right? So we decided as with single, and next we will decide which start from the 0, and still from the A1 possible choice A1, A3, A2, and we can do that with the 0 0. Cannot find it code word, so we add more symbol here. 0 0 0 triple 0 will be the A2, so triple 0 will be the A2. So it's unique. We cannot find other possible choice, and now we can come. We can write the code code word symbol is the first is the one is A4. Just to replace another. One is the A4 and the 1 0. 0 is the no choice, so we use the 1 0, which is the A1, and the 1 is A4, and the triple 0 will be the A2. So the decode will be the A4, A1, A4, A2. So we finished decode, and here's the example also shows this one, and you will see here, here, here. That is all. Can find it from the unique the symbol. Let's go. And the average codeness, which means that it is the M, which this is M. So average codeness, which we can call it as the entropy after coding. And we use the M. How to calculate the average code coordinates? We use the M and multiplied with each symbol's probability, and it should reach to the maximum entropy. However, it must like greater than the before the coding the entropy before the coding entropy. So for the symbols, we can get the code here. The high probability with has a short code length 3 bit, and the low probability with has a 4-bit with code, and we can calculate the m with 1, 2, 3. We have the total code length with 3, and here we have the 3, and for the A8 symbol, we have the 4 length because it has the minimal probability. And we also can calculate the average number of the 0 symbols. And it's well, it's quite useful for the this one, and we just we just use this M0, if the M0 to multiply it with the PAI. In this case, will be the 0.15 multiplied with 1 and M0 plus to the 2 plus 0.13 times 1. That is M0's average number of the 0 symbols. And here, so we haven't calculated the previously M. So M will be the average code word length will be the, 0.5 multiplied with 3 plus the 0.13 multiplied with 3 and 0.1 multiplied with 4, and will equal to the 1.424 bits per symbol. And for the max, which is maximum entropy, which has the 4 digits. 4 bits. So, and we will be the norm 2, 4. The maximum entropy will be the 2. So you can see the average length still smaller than the maximum entropy. Cool. And also, oh, it's wrong, the mistake here. And the average number of the 1 samples. And use this formula. And similar with previously case to calculate. And we can calculate the 0 symbols probabilities and 1 symbols probability. Use these two functions. So, and we hope it can to probability. We hope it can reach to the 0.5, right? Because we mentioned about this entropy will be the probability will be if it at the 0.5 and can reach to the maximum entropy will be the 1 bit. So that is our hoping here. After static coding, the probability should close to the 0.5, and because each symbol will has the 0 symbol and the 1 symbol can reach to the 0.5, so all of them can reach to the highest entropy. And we also can calculate some remaining redundancy and use this function. And we already know the average code length and the maximal entropy. We use the 1 minus the remaining, then we can get the remaining redundancy. After the static coding, the redundancy must be reduced by this one row. And encoded the data source as we talked before, will same as increased, and m will smaller than average will smaller than n here. Yes, previously we have the R equal to the HA with the M tau. So here, after code, we use the average code length replaced with the code word length. And it must the average code word length smaller than the code word length. That is idea. So lecture part we almost finished, and we will move to the practical part, and let's do some 10:40. Okay, and I will stop sharing.